So first of all, I'd like to thank everybody to attend this presentation, in which we're going to talk about Space Mission as a Service, or SMAS, which seeks to create supercomputers in space. This concept was actually developed during my postdoctoral studies at Universidad Industrial de Santander, so I'm going to tell you a bit more about that. And now it's managed by UbiHPC, and we are looking to bring it from concept into reality. So we're going to hear about the group, the research group in which I perform my postdoctoral studies that lead to the concept of SMAS, and we hear about UbiHPC. Then we'll go into an introduction in which I want to show you how aerospace sciences are changing from a traditional world in which we had a specific purpose software and hardware and missions, that is a space vehicle, was devised to do something in particular and only that for a while. And we're going into a next generation powered by emerging technologies in which you could have much more than that. We're going to hear about that. Then we will hear about Space Mission as a Service, what our UbiHPC will looking now to do this, and I have a personal invitation for all you attending the conference. So I invite you to look this group, Cómputo Avanzado y a Gran Escala of Universidad de Santander. They run multiple projects, and they are under the leadership of Professor Carlos Barrios, and they do all kind of projects in different fields, such as mathematics, physics, bioinformatics, and others. And now, of course, space applications. So I invite you to consider them as a potential candidate for your academic pursuits. About UbiHPC, well, we are a bunch of people who want to create unusual technology, like supercomputer of robots, or like genetic music and other technologies. Overall, we are a group of software startups located mostly in Colombia, but with some presence in the US and in Portugal, and working in different areas, from fintech, AI, deep tech, etc. And we are around 25 people. So I don't know if you guys it happened to you in the way that I'm going to describe, but when we were growing up, there were all these movies about the space exploration. You could see rockets, you could see a spacecraft, you could see robots going into interacting with aliens or whatever. And I think for most people that I have met that are involved in the space exploration or similar, they somehow were inspired by these events, by this quest that humanity always had. In fact, this is something very old. I mean, probably can be traced back up to the first humans looking into the sky and into this black background and seeing these shiny dots and thinking what is there, right? And what kind of worlds and what kind of adventures you could have if you go there or something like that. And all of that desire inspires us to create all kinds of potential applications in space, from space shuttles and the International Space Station, and exploration to many stars or planets. And it has led us to create this very beautiful and complicated trajectories to reach these destinations and to create multiple type of vehicles that could go some places that we yet cannot go. Or for example, this beautiful image in which you can see the type of trajectory that you need to have to go from one celestial body to another body by exploiting the forces of each planet. But nowadays we are seeing a phenomenon. We are seeing that all of this is being empowered by emerging technologies. Because nowadays we don't need to create something that will only do a specific purpose, but something that will go beyond that. And I want to tease your imagination into imagining what you could do with these emerging technologies if you were to apply to space exploration. And the very interesting part about this, sorry, I'm seeing in the chat that there is some issues with the audio. Can everybody hear me, or the audio is
Yes,
fully quiet?
we can hear you, but there is some background noise, maybe from your side, because all the microphones are closed.
Okay, let me get some some headset, and I'll be back one
Okay.
second to see if it improves. Okay, one second. Can you hear me better now? Hello, can you hear me?
Yep, we can hear you.
Is it better now?
I think so. We already listened that background sound, but I think it is better.
Okay, if the background noise is too much, please let me know.
Yes.
Okay, so I want us to think what we could be doing with these emerging technologies if we were to apply it to space exploration. And the very interesting feature about this is that in the past you need to have a lot of money and a lot of resources to do something in space exploration. You need to have some money to create a rocket or to a space vehicle or whatever. But nowadays you can do a lot of stuff just with your computer at home. And this is a very interesting aspect in terms of industry and entrepreneurship, for example, for Colombia. At the moment, Colombia is not a high power into space exploration, but with these new emerging technologies, we could have a dent into success in space industries. So what you can do with artificial intelligence is very interesting. For example, you can access to data from public sources, for example, from Sentinel satellites, and then process images from there using AI techniques, computer vision or else, and then use that to create some application or something you could either use for research or for even commercial activity. Internet of Things is changing the way we communicate. So nowadays it's not only about having a cell phone, but a lot of all kind of potential devices that are smart enough to interact with the internet and sometimes even cooperate among each other. So what applications could we create in Colombia, for example, to monitoring agriculture or water supply or many other features by combining the Internet of Things with the space capacity? Robotics, of course, is a long research field doing all kind of stuff. And nowadays it's even easier and cheaper to create robots that could be used in many applications, because now that you have open hardware, you have open software, you have ROS, robot operating system, you have all kind of technologies. You can embed a robot or a drone or a rover with a companion computer like a Raspberry Pi or an NVIDIA Jetson series or all kind of potential companion computers. And then you can transform these robots into smart technologies. Quantum computing is something that I believe Colombia is a bit far behind, but nowadays you can write some software in Python. Actually, I invited to read a book called Quantum Machine Learning with Python. And it's quite easy to use a library called Qiskit to run quantum computing. And you don't need to create a quantum computer, right, to use it, but rather you can connect to IBM quantum computer or AWS or whatever, and then use this Python software to create some application that might be useful. Cloud computing, of course, nowadays you don't need to buy a lot of servers and maintain it and hire people to take care of them. You can go really quickly to creating a product and launch it to the market. This is very interesting. Of course, there is a technology dependency, but that's a discussion for another time. But overall, with this existence of computing power in the cloud, you can go into the market really quickly, something that was not possible before. Now, augmented mixed and virtual reality. I imagine a world in which you can just plug some headset, some Oculus, some HoloLens, or whatever, and you can see what is happening in another continent because you are connecting to a satellite, and the satellite is showing you what's happening there. Of course, that might generate a lot of privacy issues, but if it is managed, it will be something very interesting. Blockchain. Now, how to combine space exploration with blockchain? For example, at UbiHPC, we are creating a product called Trust in Space, which attempts to store data from spacecrafts into a blockchain in order to provide traceability, in order to create a better understanding of a digital twin of space navigation. And I'm sure many applications can expand from blockchain if we go from the mentality that everything has to be centralized into a wallet in which everything is decentralized and then it does not depend on a single control. And of course, many more things could impact the way we do space exploration. And I want to show you some videos of some cool applications of already smart vehicles operating that are packed with companion computers like those that I was mentioning, and that are showing the potential of all these technologies. Can you confirm that you can hear? Do you hear the audio?
Right.
So this is very interesting because if you can see that we have already a multi-robot system operating in another planet. And the interesting thing about this, well, just at the moment it's just a demonstration, but in the future we could even create a supercomputer robots. For example, we could have, since each of these robots will have a companion computer or some general purpose computing capacities, then there is no reason why we cannot create a supercomputer. And therefore combining the computing power of both of them to do something that will be rather computing complex and not depending on downloading that to Earth. I want to show you some other video of the JPL Nebula software.
Kids are really important for NASA because they might be the key to find an answer for humanity's long-standing question of if there is or was life in other planets. In today's demonstration, our main success metric is if a team of robots can autonomously explore hundreds of meters into a Martian outward cave. When integrating autonomy and AI on a physical robot, it's really important that the robot supports the requirements of stability over difficult terrain. At the same time, it's really important that the robot is capable of carrying science instruments while it has necessary endurance and speed. Boston Dynamics Smart Robot is one of the few that satisfies these requirements simultaneously.
Today, first thing we're doing is setting up our base station. Then Spot, our robot, enters the cave. Very next step is let's get communications, so Spot can keep talking to the base station. And then the robot explores by itself autonomously. As it does, it sends back information, which is a 3D map, which we see on the base station. And then if it detects things that are scientifically interesting, that may be indicative of biofilm, it sends those images and its location in the map back to the operator. And here's where the team of robots comes in. Robot number 2 has a robotic arm. And that robotic arm is a really capable device to get very close to the wall. That can allow us to get more information. The still it might be some type of biosignature. It could take out a swab and take a detailed sample and put that in an instrument to take analysis of the chemical composition. Additionally, it could shine a certain type of light that could assist our robot number 3. And robot number 3 can come in with a more advanced camera that can zoom very close, that can see in different spectrums. We have these multiple mobile robots that can carry different instruments as opposed to one big robot that's going to have trouble traversing in this terrain.
Okay, let's come back to the concept.
So I'm showing you this video because I wanted to imagine that a supercomputer does not need to be necessarily as it has been traditionally understood, right? So originally a supercomputer was created to take a bunch of servers, combine them, so you can exploit the computing power that would result of running all these machines. Because it was not possible to put more computing power into a single computing machine, so you could just plug a bunch connected to a high-speed network and install a set of software layers that would make them act as if they were one. But precisely is there when we can go beyond high-performance computing, because you have a bunch of units that behave as if they were one, and therefore they can cooperate to do all kind of stuff. Yes, they can combine the computing power so they are more powerful, but they could also do more stuff, like we have seen in this video. So first you send a robot that could do some preliminary scan. Then you send another one that can do all kind of old sample taking or whatever. Then you send another with a powerful camera, and all of this could be done by exploiting this combination of computing capacities. And that is not the only thing that I want to mention here. There is already happening some interesting applications, like, for example, the Astro-V robots. These robots are operating in the International Space Station, and they are helping with astronauts with common tasks, like monitoring some services, etc. But the interesting thing about them is that this already is coming with a computer on board, and this computer is running an operating system, a common operating system, like a Ubuntu probably. And therefore, you can use this robot for many things, and to reuse them, and to load new software, and to use it for something else. Again, a feature that is common in supercomputing, where you have a multi-purpose, multi-user infrastructure that can be used for different stuff, and by connecting directly to a master machine. And that's not the whole thing. For example, ESA has the Astro-Pi computer, which is basically a Raspberry Pi that has been included with some sensors and with some capacities to survive in space. And the idea is that young people on Earth connect to the International Space Station to these devices to perform some experiments. So we can go even further from there. Recently, Lockheed Martin and the University of South California launched La Jumeau satellite. And this is a very interesting vehicle because on top of having the traditional capacities for navigation in space, etc., it has an NVIDIA Jetson embedded in it. Of course, it's a computer that is designed to support space radiation and other issues in space. But the advantage of packing a satellite with this machine is that now you can process or pre-process data on board with the machine. You don't need to download all the data into Earth. When you want to download something from space, you have to have a line of sight between your ground station and the communication systems in the vehicle. And that connection does not happen all the time. So only during some moments in the day, and this depends on the orbit of the vehicle and many things. In some cases, you need to wait for several orbits in order to download something useful. But if you could process data on board of the vehicle, then you could download only what is interesting for you to observe. That is the power of packing some space vehicle with general purpose computing power. And in the end, we can go further than this. Hewlett Packard Enterprise, in cooperation with NASA, launched the Spaceport Supercomputing. This is a machine that has around 1 teraflop of capacity, and it was sent into the International Space Station. The objective is that complex simulations can be performed there, and eventually, when we are traveling to other planets, you could rely on a lot of computing power to do all kind of simulations on board of the spacecraft. This was developed to support exiting and re-entry from Earth atmosphere, and it has proven to be successful to run computations in space. So we are going from a world in which everything was devised for a specific purpose, in which you had hardware and software that was made for a particular mission that was being run. And then after the mission was finished, then you have a vehicle that will stay there, sometimes for hundreds of years, or it will eventually re-enter Earth, but it will become eventually garbage that nobody can use. Actually, that's a big problem nowadays. We have too many garbage in space, at the point that at some moment something really bad could happen to us, from losing communications all over the world up to a very bad scenario in which we are trapped in Earth and we cannot leave anymore because some collision would create a domino effect that will create so many small particles that will prevent us to go outside Earth. So that's something that is a lot of issue. But if we could reuse the vehicles, or if we could change the purpose of the doing, then maybe the situation could improve. So we go from this world of specific purpose into a world of general purpose space computing, general purpose computing in space. And what is the idea of that? So you have still the subsystems in a space vehicle, like communications, propulsion, navigation, etc., but you combine that with a companion computer. At some moment, maybe we could have this computer also controlling the subsystems in a space vehicle. But nowadays, these devices are not made for that purpose. So by combining them, you could have a powerful architecture. On one hand, you have the core computer, which will take care of controlling the subsystems, but you have a coprocessor that will aid in processing data, like images or whatever. If that becomes a reality, Then eventually at some point we can think about supercomputers in space in the traditional sense, in the sense that you can combine the computing power of all of them. But of course that depends on having communications, TCP/IP communications in space and having internet in space and all of that. That to my knowledge is still not sufficiently stable, but at some point that might happen. At some point we might be able to combine computing power from multiple space vehicles, and I'm talking about satellites, but of course this will make also sense if when current return to the moon, when we have multiple rovers exploring the moon, maybe we could create supercomputers between them. But even before that moment arrives, when we can combine the computing power in space, we still have something very interesting that we can take up, we can take advantage from the world of supercomputing, and that is the concept of reservations. The capacity that you have a user connecting to a master node, and they may be being able to request the utilization of X nodes or X cores or certain amount of RAM or X amounts of GPUs or whatever, to take a bunch of hardware and use it to run a particular software for some time. This concept of reservations is what brings the world of the concept of space mission as a service into reality. So, what space mission as a service or SMAS is trying to solve? If you are NASA, if you are ESA, or if you are SpaceX or whatever, and you have sufficient money to send some constellation of satellites, or you can send some robots into space or whatever, then it's fine. You can make exploration, you can make industry, you can do all kind of applications in space. But if you are a startup or a small country or a research group or anything, you have to rely on existing open source data. Otherwise, you cannot do anything because you simply don't have the money to send them, right? But it would be interesting if you, being whatever you are, a small startup, a country, or whatever, you could selectively collect the data that you want, not just accessing the data that is available, but rather to command the vehicles to get some data for you that you would need for some particular application. Also, think about this: when a spacecraft is performing a mission based on some orbit and is designed to, I don't know, to analyze data in some particular location, all the time that is not on that location, it's not doing anything. It cannot do anything because it's simply not in the place. But if during that time that a spacecraft is not doing what it's supposed to do, could be used for something else, then we could reutilize the space vehicles. Maybe at the point that we don't need to send more vehicles of the already existing, but rather to use the ones that are already operating in there. So imagine a world in which you just are with your laptop and you say, I need a couple of nano satellites when they are flying over some particular location, and I want them to have some camera or whatever, and I want to make a reservation of them and use them to detect something and then publish that to an app or whatever, so you can monetize your technology. Or you want to do some research, maybe you want to log into the Astrobi robots in the International Space Station and use them to see, I don't know, to help manually the astronauts, or to have an experience in which you are commanding a robot in space or whatever. That is where, to satisfy or to get to this point in which you could selectively request resources in space and combine it with resources on Earth, is what Space Mission as a Service is looking to do. So what's the idea? The Space Mission as a Service applies to existing and new spacecraft. On one side, the existing spacecraft, they don't have general purpose computing power. They don't come with a companion computer that you could use to do something that they are not pre-developed to do, right? But they could get data, and if you could maybe somehow take control of them over some moments of the operation, maybe you could get data from them. The data is not going to be pre-processed on the space, but you could selectively get data from them. Now, if we talk about the new spacecraft that are going to be packed with general purpose computing, then you can do all kind of stuff, right? You could do local AI, you could do data pre-processing as we talked. We could do even vision-based navigation. NASA is creating a probe that is looking to land on an asteroid by seeing, instead of relying on a pre-programmed trajectory. Rather, we'll use computer vision techniques to land on a hazard. We could do, if you give a space vehicle vision capacities, we could do autonomous collision avoidance and much more. Basically, imagination could be lead us to do all kind of stuff. So the idea is that you have people requesting something in space. They want to get some whatever, some control of the some vehicles or some data that there is not available, or even data that is available. We will see a bit more of that. And then you will interact with a service that will connect you to these vehicles in space, and do the same as a supercomputer do. Make a reservation, and then you get the control of those vehicles, of those resources for some time during the operation. So the solution to this problem of actual true democratization of space will be to use these reservations of space resources and also combine it with computing power in space and in Earth. So what are the advantages of this? As I was mentioning, true space democratization. Real access to a platform in space. All kind of new business models could emerge from this, because now you don't depend on owning the vehicle to do some space exploration, but rather you can rent it for a bit. And overall, a new space platform for general purpose research. That means that imagine that you're not only accessing one vehicle, but you're accessing multiple vehicles at once, and then maybe you can take some image which belongs to different operators. Let's say you have some spacecraft from NASA, some from ESA, some from SpaceX, some from I don't know, whatever, and then you can get one of these and one of this and one the other, because they are located at some points that you're interested, and then get data from combining their operation. That is something that is not done. In fact, there is little cooperation between space carriers. I don't know if you were aware, but recently there was a potential collision between one of Starlink satellites and the Chinese space platform, because simply information was not shared in a timely manner. Therefore, there was potential issues. So there is no cooperation between these space operators because of privacy concerns. All of the space is very tightly defense and all kind of stuff. So it's very difficult. But with this approach, you could have a space platform to do all kind of applications. So to give more context to this, the idea is that you need a network of ground stations, and this is an issue. Imagine that you are a Colombian startup and you want to launch a satellite into space, and then you need something to communicate with the satellite, right? You need a ground station. But as I was mentioned, only when there is a line of sight between the ground station and the satellite, you can do some command and control. You can get some telemetry, download payload data, whatever. Only when there is a line of sight. Therefore, it's complicated. On top of that, creating a ground station might be expensive. You need people to operate it. It's complicated. But if you can have access to a network of ground stations located in different parts of the world, and then selectively accessing them, then you could increase the number of contacts with the vehicle and therefore increase the interaction with it. So the first part of the of the SMAS concept is a piece of software called the SMAS Master. The idea of this service is that the users will interact with it, and this service will talk with the network of ground stations in order to have access to the vehicles. All kind of agreements could be made. For example, NASA could do an agreement in which they download data that is not processed and up to some wavelength or whatever. Then SpaceX could provide, I don't know, maybe some already processed images or some already processed sensor data. So all kind of different levels of access to these satellites could be, or these vehicles could be provided. And I'm using the word satellite a lot, but let's go beyond that. So I'm talking about space vehicles. So it could be robots, it could be space telescopes, it could be anything that is in space. If you can interact with them selectively, then you can download data, but you could also upload data that you need to use something on there. And actually, you could even change the software that is running. If you have a companion computer there, then you can maybe even connect and upload your own software and to process the data that is being collected from a camera or a sensor. Overall, the users could create a space mission workflows, which means data collection, either in space or in public or open source space repositories, processing there in space if you have the capacity, otherwise processing on Earth and then expose the results for some particular application. As I was mentioning, it's not only about collecting data from space, because there are already data that is being collected in some particular repositories and some APIs and something, so you don't need also to actual data. So this master is devised to be able to interact with space resources, but also to collect data from Earth data centers. And then the interesting part of when you finish this space mission workflow is, what do you do with that data? Okay, if you want to do just research, maybe you just need to collect the data, process it, maybe send a publication, that's fine, right? But if you want to create some autonomy, some autonomous services that can take data from space and do something with that, maybe you can launch that into some services. And I'm referencing AWS now because we at UbiHPC been working with AWS for quite some time, but not to, so there are other options. You can go into Google Cloud, you can go into Azure, you can go into other solutions. But what do you do with this data? Well, you might need to storage, so you might put it in S3. You might want to create databases for this. You can use DynamoDB or others. And interesting, you could take the data and create some pipelines that collect data from here or from here, and then go into a model that has been deployed over Amazon SageMaker, so you could predict something based on that data, something that is happening with some, I don't know, maybe there is a potential fire occurring someplace, or some tracking of wildlife, or whatever that you want to use some classification algorithm. You could deploy it on SageMaker. And then maybe you can expose these findings via a GraphQL API, so other apps or other people or whatever can connect to your processing, to your results. So the interesting thing about this is that you are creating a full service collecting data from space or from Earth, and then storing it, processing it, and then exposing it to the people. Now, for next generation spacecraft, we can go further and deploy a sort of agent in each of these companion computers. So that agent has the capacity, for example, of uploading new software, or maybe even changing the navigation capacity of the vehicle for some particular reason. Maybe this will apply better if you're already on the moon, for example. You want to connect from Earth and then navigating manually with a rover that is there. Something like that could be done if we have a client deployed over the companion computer of that vehicle that is interacting with the navigation capacity, just as it is on Earth with any drone or rover. And with all of this approach, we are transforming effectively all of these vehicles into a simple IoT device. Well, simple, I mean, in comparison with other IoT devices on Earth, but with capacities for intelligent processing on board. Now, a simulator of this software was made, and I want to show you a video about that.
Space Mission as a Service, or SMAS, is a new idea which seeks to replicate two concepts in the world of space applications. The first one is to consider any and all space vehicles or entities as IoT devices capable of local general-purpose computing. How can this be achieved? By embedding a satellite, a probe, a robot, or else with a general-purpose computing device, such as a Raspberry Pi or a GPU-powered NVIDIA Jetson series card. By doing that, our entities will become capable of local AI, data pre-processing, optimized space Earth download bandwidth, vision-based navigation, autonomous collision avoidance, and much more. The second concept emerges from the first one. If we have a set of space entities, all capable of local general-purpose computing, then we can deploy a supercomputer in space. That is what SMAS is all about. Universidad Industrial de Santander, in Bucaramanga, Colombia. Software in the loop, because in each.
So I wanna move it a bit forward so you can see what is the idea. So the idea is that you have the simulator. What it's looking for is to demonstrate the concept of having multiple vehicles that can be accessed from Earth, as we were talking before. So imagine you have a bunch of satellites. The idea is that a user will be able to request the use of this. So let's see it.
Where each is capable of local general-purpose computing, contributing to the creation of the space IoT. Here, you can see the orbital parameters for our nanosatellite. feature.
So think about this. Each of these, just like in any common supercomputer, you have a group of nodes. Each of these nodes has a quantity of CPUs, an amount of RAM, maybe some GPUs, some CM5, whatever, other capacity. But in this scenario, then you have something more than that. You don't have only computing power, but you have, for example, cameras, you have different sensors. So you may have a satellite that have maybe a hyperspectral camera or a multispectral camera. Others that will have some particular sensor. Others that might have computing power on board. So resources in this scenario goes beyond computing power into something else. And this will allow you to select what you want, right? So it's not just about I want some raw computing power, but rather I want some computing power, but packed with some specific perception capacities, like a particular camera.
Features a hyperspectral camera, and of course, the GPU NVIDIA Jetson card, which later will be used for fire detection. Right now, our entity is without any assigned requests. We will talk about that later. Also, we can see the nanosatellite's telemetry, its position, velocity, and data related to the companion computer, the NVIDIA card, such as RAM, CPU, GPU, and energy consumption.
It was software in the loop and hardware in the loop simulation that was run at the University of Santander. The idea is that we have a bunch of NVIDIA Jetson Nanos, and each one was representing a space vehicle. And therefore, we were simulating as each of them were interacting, that you will be able to upload software and to run something on them. So, and we use some simulated orbits from some vehicles, like an International Space Station and another satellite and other vehicles. And this is what you're seeing in here. You're also seeing the features of the hardware consumption, like CPU temperature, GPU usage, etc.
Let's check now the vehicle's real-time location. You can see it right at the top with the blue box icon.
You can see it in here. Now, let's see
A set of interconnected tasks.
the concept of reservation. So, reservation will actually, so it will be the result of running a space mission workflow. The idea is that you will have a set of tasks. Those tasks would be of type space. That means something that will be executed in space, or something that will be run on Earth will be a type data. What you want to do with that data? In this case, with AWS.
Where a vehicle is assigned to a user space entity.
So we created a language to describe this space mission workflow, and therefore you can write that template and launch the request
of a
specific resources in
that
space.
is executed on Earth with a data language which allows a user to specify requirements, such as features of specific vehicles in space, the execution of a selected software in an entity's companion computer, access to AWS services such as S3 for storing the data collected by a vehicle, all of this and much more. Let me show a complete example. We will request a space mission workflow composed of two tasks. The first one of type space, which will be executed in the nanosatellite with a polar orbit. The software executed in the space vehicle will be used to detect fires by using a computer vision algorithm applied to satellite imagery. The second task consists of uploading the pictures, where fires are detected, to Amazon Web Services S3. Let us go to the entities view to check upon the nanosatellite 1. As you can see, the entity is now occupied. We can see information related to the space mission workflow, such as the monitoring of each of the tasks. Also, we can see the live feed of the images processing. While we wait for the task to be completed, let's check out the details of the tasks. As you can see, the data S3 task is linked with the fire detection task. That means it will be executed immediately after the first one is completed. Now, we can see that the first task has been completed. Let's wait for the second one to be finished. All done. Let's go to S3 to check. As you can see, the pictures have been uploaded automatically to AWS S3. Also, now our mission is completed since both tasks are finished. Therefore, our nanosatellite is ready to be reassigned to another space mission workflow.
So the idea with this simulation was to pretend that we have a satellite that we could request from Earth to do some processing of fire detection, and then process the images on board the satellite, then download the results of those and upload the image into an AWS service, in this case S3. So creating, as I was mentioning, a workflow from data collection in space up to exposing the data for some particular application. I think I don't have much time, so I'm going to skip a bit the next few slides, but I want to mention a bit about AWS ground station.
Space mission is
So the main concept that I want to, when you need to keep in mind, is that this, when you think about the reservation in a HPC cluster, a supercomputer, you're talking basically about hardware, like how much hardware you need, and maybe some software environment, right? You can have some specific software that you need for your particular job, and maybe you need something for bioinformatics or whatever. But when you, yes, I will share the link in a second. But when you're talking about SMAS, you want to go beyond that, not only to request something based on the hardware that is available. Like first of all, this is what we call resource-based. So hardware is not anymore only computing power, but you can have all kinds of sensors. Actually, all of these ideas come from the concept of high performance robotic computing, which basically is the same, but rather with robots. And then in these IoT devices, robots or satellites or whatever, you have more than computing power. You have some sensors, you have some actuators, or something that enhance this concept of reservation. But also there is another interesting issue, that this reservation might be based on location. So you have, maybe if you want to do something over the North Pole, like process some data from the North Pole, whatever, you don't have use for the vehicle when it's not there, right? So maybe you want to do a reservation based not only on what hardware is available in there, but rather where the vehicle is located, and to do it before, so once it's there, you could actually take control of the vehicle. Another main concept that I wanted to leave you is the concept that with this approach, now we don't have spacecraft. Now we have space IoT devices and general purpose space IoT devices, and therefore you could do all kind of applications. Now the main components of this infrastructure are the following. On one hand, you have this mass master service that we were talking about, and this is like a augmented ground station. It's not just about getting telemetry from the vehicle. It's not just about sending some command and control. It's about using the vehicle and reusing the vehicle for other applications. The idea of this service is that it's composed of some layers that, first of all, has an interaction layer that is to control this network of antennas that, as I mentioned, I'm going to tell you a bit more about AWS ground station, which I think is very interesting. And then also the interaction with data services, capacity. Then you have the Earth communications layer and the space layer. All of these layers is what we call the back end of this space mission as a service concept. The front end will be some app, web app, or mobile app that interact with the smart master in order to provide the capacities for the users to selectively control the space resources. Now, in regards to the interaction layer, it comes with two sublayers, the control sublayer and the data sublayer. The idea is that the control sublayer will interact with this network of antennas in order to be able to connect with this space vehicle and to interact with the services to provide what to do with the data afterwards. And here is where I want to talk about a bit about AWS ground station. So the very interesting aspect of this service is that, as I was mentioning before, having a ground station could be something complicated, right? So you have to spend some money creating it, you have to administrate it, you have to scale it. If you want to have access to multiple, if you want to have multiple contact with a vehicle, with a space vehicle, then you will have to have a network of antennas. And this is what AWS Ground Station provides. So they basically put an antenna close to each region. And therefore you can have multiple contacts with vehicles because they are located in different parts of the world, and therefore they could see the vehicles more times than it would be just to have it in, I don't know, in Colombia, let's say. You only pay per minute, I think it's $12 a minute or something like that. You can schedule your contacts, you can say when that is going to happen. This match up a lot with the ideas of Space Mission as a Service. You have a FIFO approach, and you have support for multiple different type of vehicles operating in different frequencies. And something very important, it performs auto-tracking during context. Anyway, just to mention that this service could be very interesting for the deployment of Space Mission as a Service. I'm going to move forward with this because I believe I don't have much time. But at the moment, Space Mission as a Service is a concept. We at UbiHPC want to make it into a reality. And therefore, if there is somebody out there belonging to NASA, ESA, AWS, or NVIDIA that maybe finds this interesting, maybe we can talk about to see how could this be tested or in reality. Finally, I want to make an invitation to all of you here. It is a personal dream of mine. I believe that it's a dream of many people in the country to make of Colombia a powerhouse for technology, right? And the space is one of those fields in which we don't have much information. So at the National Space Society Colombia, we are trying to accelerate that. So I invite everybody to join maybe to this association. It's a non-profit organization that looks to develop space exploration. And finally, I want you to imagine all the things that we could do with these emerging technologies. You don't need anymore to have a bunch of resources to create something really cool. And all of you out there that are doing all kind of cool stuff, I invite you to consider what can be done with the current resources that you have by exploiting these emerging technologies, either and combining in some way between HPC and space exploration. Thank you so much, and if you have some questions, I'll be happy to hear it out.